we are going to take a look at normal distributions and the central limit theorem. And oops, it is not lab 7, it is lab 8. So part 1, this relates to normal distributions. Suppose that you are an elementary school teacher and you are evaluating the reading levels of your students. You find an individual that reads at about 50.2 words per minute. You do some research and determine that the reading rates for their grade level are normally distributed, we'll look at that in a sec, with a mean of 90 words per minute and a standard deviation of 20 words per minute. So some measurements are normally distributed and some are not. Normal distribution is a type of distribution. It is symmetric, it is bell-shaped. There are many symmetric distributions, there are many bell-shaped distributions, there are many distributions that are symmetric and bell-shaped, but there's only one group that are called normal. So let's take a quick look at a normal distribution. So a graphing calculator I like to use called GeoGebra. I said make me a normal graph, and this is what it gave me on the default scale, this blue line here. I'm going to just change the view of that a little bit. And we've seen this shape before. We've been drawing it for a little while. And I can distort this shape. This is the same graph I was looking at a minute ago. This is a normal distribution with a mean of 0 and a standard deviation of 1. And I can make it look flatter or taller and skinnier just by changing the scale of the graph. All right, so let's say that's a good looking normal distribution right there. Let's make it just a little bit bigger. Okay, now a normal distribution has a mean, and I can shift that mean by moving it left and right. Ooh, off the screen. Now notice it keeps the same shape, so here I got the mean over around, let's set it at 3. Oh, it's very hard to move, isn't it? Okay, so that's close to 3. Still has a standard deviation of 1. Standard deviation talks about the spread of it. So if I make the standard deviation narrower, then it becomes taller. If I make the standard deviation, standard deviation is getting smaller here. So here's a standard deviation of 0.5 versus 1. And then a standard deviation of 2. It's about right there. Okay, and I kept the mean the same at about 2.9. So standard deviation talks about the spread. Now, as I move the mean and change the standard deviation, one thing that remains true is there's an area between this blue curve and the x-axis. And for a normal distribution, that area is always 1 for 100%. And the areas represent probabilities. Okay. So again, to maintain that area of 1, as the standard deviation gets smaller, the peak has to get taller to keep the same area. Kind of a weird idea. And if we just change the mean, then that doesn't do much. So let's see, I'm just going to play around here. Let's look at a different, easier to use system. So here, StatKey gives us a graph of a normal distribution, and it always looks the same shape regardless of what we pick the mean and the standard deviation to be. So for example, here I have a mean of 0, standard deviation of 1. This is called the standard normal distribution. There are many other normal distributions, like if I edit the parameters, the reading scores for kids at that grade level were 90, and the standard deviation, I believe, was 22. So I hit enter, and now the mean is set to be 90. Notice that's right between 80 and 100 on this bottom axis. Standard deviation is 22. Standard deviation, one thing that's true of all normal distributions is that if you were to say, look, one standard deviation on each side, so 90 minus 22, that would give me what, 68 would be the left number. That would be one standard deviation below, and 90 plus 22 would be 122. We're always going to get about 68% of the data, the population in this case, that lives within one standard deviation of the mean. So somebody with a reading score of 68 at this grade level is one standard deviation below average. Somebody with a reading score of 112 words per minute is 1 standard deviation above average, and I would expect that almost 70% of individuals, kids at this grade level, should read somewhere in this range, number of words per minute. Now I can ask other questions like, suppose somebody reads at 100 words per minute, what percentile would that put them in? And that percentile is always a left tail, and I just set the x value to 100, and that tells me somebody that reads 100 words per minute is about the 68th percentile. I could go the other way. I could find out what reading score would be the 90th percentile, so I enter 0.9, and I see the 90th percentile for reading scores is about 118 words per minute. Okay. The 50th percentile, the median, well, that would be the same as the mean for a normal distribution. So if I set this to 0.5 for 50%, I should get the mean, which is also the median for a normal distribution. The mean and the median match because this is symmetric about the mean. That's when the mean and the median line up. If the mean and the median do not line up, then we have some bit of skewness. So this is a normal distribution calculator. So given an x value, I can calculate a probability. Given a probability, I can calculate an x value. When I go the other way, given an x value finding a probability finding an x value, that's called an inverse normal calculation. And we'll do a couple of each of those this week. All right, so let's take a look at this problem. So back to the problem. Let's see, 90 words per minute, 22. All right, so what are we going to do next with this problem? Well, let's take a peek. I think I accidentally made a copy of this page. Yeah, interesting. Whoa, what happened there? Oh, it crashed. Damn you. All right, let's open that back up. And find, no thank you, my last one. This one, there we go. Okay, here we go. So, question. At what percentile is the child's reading level? We just looked at how to do that, and we want to create a graph with a normal curve that illustrates this. So, StatKey can do both of these. It can make the graph and calculate the percentile. So, let's give it a shot. So, we already have the mean set up, right? 90 and the standard deviation of 20. Next thing we need to do is a left tail, because that's a percentile, with this child's score, which was 50.2 words per minute on average. And that puts them in about the 3rd or 4th percentile. Notice they get a probability of 3.5, which would be, 0.035, which is 3.5%. So we'll call it about the 4th percentile. So let's get a screenshot of this. All right, so here's my screenshot, and let's write on it. So this right here would be approximately the 4th percentile. So again, the area under a normal curve represents a probability related to some x value. In this case, the x values are reading scores in words per minute. Okay? So I should probably write out some kind of sentence to go with that. So let's get a new page. So let's see, a child with a reading score of 50 words per minute is in the 4th percentile and then we should also say where the average for this age is 90 words per minute with a standard deviation of 22 words per minute. Okay, so what does it mean again to be the 4th percentile? It means, let's switch colors. I got that color. Only about 4% of children this age read at a slower rate. All right. So I would need to talk to the parents because this is a concern. So what would I tell them? Well, given that there's data on this from all across the country or world throughout many years, we know roughly how the reading scores are distributed, about what percent of kids read around the average and what percent of kids read way below the average or way above the average. And it turns out it gives us this nice symmetric bell-shaped curve. So we expect most kids to read somewhere between 70 and 110 words per minute, right? That's in the middle. About 70% of kids will read in there. And this child, only about 4% of kids read slower than this child. So 96% of kids read faster than this child. So we're a little worried about the child's progress because reading is one of the most important things for all other aspects. And so the rest of this particular problem is for you to write up what it means to be normally distributed, how this tells us the kids in the 4th percentile, and why this is a problem. What a 4th percentile means. All right, so I'm going to leave you to finish that one up and think about it. Next question. Now this one relates to the central limit theorem. Central limit theorem is a bit different. Central limit theorem is related to sampling distributions. So if you're not quite sure what a sampling distribution is, I have a couple of videos on that. Please look them up in my playlist. So sampling distribution means we're looking at a distribution of sample means, not a distribution of individuals like we were looking at here. Okay, this is a distribution for individual children. Now I want to look at a distribution of samples of size 55. And sampling distributions tend to be normally distributed. Okay, that's important. And calculating the standard deviation, we have an extra step to do that. Now, we're told that the Federal Food and Drug Administration here allows a certain bit of contaminants to be in your milk. If it's over a certain amount, it's not healthy to drink the milk. There's always contaminants in your milk. There's always contaminants in your water. That's a given. The question is, when is the threshold for too many contaminants that it's going to hurt people? So they say as long as the average is not more than 750,000 pus cells per cubic centimeter. By the way, a cubic centimeter is about the size of the tip of your pinky, so just a little, several drops of milk, with a standard deviation of 126. So here I actually need to consult a calculator before I can consult StatKey because I have to calculate a special standard deviation. This is the standard deviation for an individual sample of milk. What I'm looking at now is what about samples of size 55? Okay, so 55 individual 1 cc samples. Now I have to employ the central limit theorem. And what the central limit theorem says is that the mean of the sampling distribution, right, so we're switching over from a regular distribution to a sampling distribution. Why are we doing that? Because we're talking about samples now, not individuals. So anytime you start talking about samples instead of individuals, you have to adjust a couple of things. So sampling distribution. First important thing about a sampling distribution is the size of your sample. I have n equals 55. Now the mean of the sampling distribution, we call that, let's use the proper symbol, mu with a subscript x bar. Okay, so that means the mean of sample means, and that's the mean of a sampling distribution, is approximately equal to the mean of the population if your sample size is big enough. Okay, sample size should be at least 30. I have 55. That's good enough. So in this case, the mean of my sampling distribution is going to be approximately 750,000. The standard deviation of the sampling distribution. That would be sigma with a subscript x bar to indicate I'm talking about sample means, a sampling distribution, a distribution of sample means, is going to be approximately equal to the standard deviation of the population, if you happen to know it, that's a whole nother problem, divided by the square root of the sample size. So in this case, to answer questions about this, I need to adjust the standard deviation because I am playing with a sampling distribution. So I take the population standard deviation, 126,000, and I divide it by the square root of 50, and let's seek a calculator for that. I have a spreadsheet here. Now let's blow that up again. All right, so this is my population mean. Right. Population. This is my population standard deviation. This is my sample size, n. And this is the Central Limit Theorem standard deviation, which applies to a sampling distribution. It's a very important distinction we have to make. And I found that by taking the population standard deviation and dividing by the SQRT, the square root of the sample size. And when I do that, I get 17,819 to use as a standard deviation instead of 126,000. Okay, and oh shit, what did I do? I'm going to copy that. All right, let's take that into my workbook here. 17,819. So this is about, and that was a rounded amount, 17,819 is the standard deviation for the sampling distribution. So we're going to have to make a distribution for that. So my mean is 750,000. All right, let's see if I can remember all that. And I'm going to switch over to, and I'll show you this calculation later. Let's go back here. So first, what we're going to do is edit the parameters to show you what the distribution looks like for individual samples of milk. So 750, 1, 2, 3 is my mean. If these were individual samples, a single individual sample, I would look at 126,000. And so the middle is about, right here, 750,000. And you can see that gives us, within 3 standard deviations, a roughly 400,000 over to maybe 11,000-ish. So when we get milk from a cow, the FDA says that the pus samples in a CC, that most of them should be somewhere between 400,000 and 110,000. Sorry, 1,100,000. The average should be 750,000 is what we should expect. And over a certain threshold, they say, no, that's too contaminated. You got to do something about it. Clean it up, fix your cows, whatever. If I look one standard deviation on each side, so if I add 126,000 to 750,000, what will that give me? That would give me 886. So two-tail. 886, 1, 2, 3. That should be one standard deviation to the right. Ooh, I messed that up. 7 and 1 is 8. It should be 876. 876, 1, 2, 3. So that's one standard deviation to the right. And look at, there's that 68.3% again for that middle chunk within one standard deviation. So as long as a distribution is normal, doesn't matter what the mean and the standard deviation are, within one standard deviation on each side, you should always find 68.3%-ish in the middle. All right, so notice the spread of numbers here, 400,000 on the low end here, 1,100,000 on the high end. Now that's when I'm looking at single samples, but now I'm looking at samples of size 55. So now I have to edit the standard deviation to deal with the sample size, and that was 17,819. is the new standard deviation, and what that does is it narrows this quite a bit. So now, instead of going down to 4,000, I'm only going down to around 7,000, and before we went up over 1 million, and now we're only getting up to 800,000, because we have a narrower spread, a smaller standard deviation. Okay, next. What did the question ask? You collect a random sample of 55 specimens, each of 1 cc. which results in a sample mean of 772,166 pus cells. Okay, so that's above average, right? We were expecting that the average should be 750,000. This is above average. So we want to measure, well, okay, how unusual is it to get a number of that size? All right, so let's plug it in. So since that's above average, that means I'm doing a right tail. If it was below average, I would do a left tail. And then I enter my number, which was, again, 772,166. 772,166. Enter. And I find that almost 11% of samples of size 55 will have a mean of 772,166 pus cells per 1 cc or more. Okay, 10%. Now, what's our usual cutoff for unusual events? Well, usually we say 5%. So this is 10%. That's not that unusual. I mean, it's not a high probability, but it's not that unusual. So the question is, does this sample support the FDA's claim? What's the FDA's claim? The FDA claims that the average should be 750,000 and the spread should be 126,000. Does our sample defy that by being way unusual? Answer is no, because 10% is high enough. In other words, this mean is close enough to the mean of 750,000. Okay? So, is this a lot of pus cells? Yeah. Is it significantly more than should be expected for a size of 55 cc's? And the answer is no, it's not. It's only 10% of samples have more than that. If this number was up here, like suppose we did a sample and we found there were 800,000 pus cells, well then it's less than 1% of samples should have that. Now this is unusual, and either the FDA's mean is wrong, or there's something wrong with my cows. They're a little too contaminated, a little too sick. Okay, so you now have to think about the consequences of this sample based on what the FDA said to expect, and so you have some questions to answer about that. All right, so I get you started there. Answered the first few questions. You have to answer the rest. Good luck. Read this carefully. Think about it. Find a friend to chat with. That's it for now. Do good math.